All right, next up, how we do control in assembly. This presentation is labeled part one, but really this will be pretty much what we're going to look at in terms of control for the time being. So the activity that you're going to do after this presentation is in the ASM activities folder 5 control. Now this particular presentation really has to do with simply sections 3.6.1 and 3.6.2 in your text. And we're actually going to skip 3.6.3 through 3.6.6, which do explain a little bit more about if statements, but we're going to skip that this time. And we're also going to skip both loops and switch statements in the rest of section 3.6. So we're just going to concentrate on the beginning of section 3.6 here. And then here we have our, just so you remember, our kind of picture of what our CPU looks like, and that data is moving from memory into the registers, and here's our program counter that keeps track of things. And in fact, we're going to add 4 little bits today and think about those. So first off, we want to remind ourselves what a relational expression is. We're going to be basically trying to compare two values, whether they're in variables or whether they're constants like this. And where do we see these things in our code? Most often it's in things like if statements. So here we're taking this relational expression and putting it in this if statement here. This same kind of expression could be in a while loop. So you might be doing something like this. It also could be in a for loop, where now it's it's the test right here in the middle of the for loop. So these are common examples of these relational expressions. So we're going to see how these work in assembly, how the compiler is able to return true or false, i.e. 1 or 0, for these kinds of expressions. So let's remind ourselves again of some of the state that we can have in the processor. So the Intel x86-64 register called RIP stands for instruction pointer. That's the same thing as this program counter that I've been showing in various abstract views of our computer. And then, of course, we've got all these registers to hold temporary data. And the thing that we're going to concentrate on now today are some single bits, 1-bit values called condition codes. And we haven't talked about these before, but we're going to see how these get used to evaluate relational expressions, along with some new instructions that you're going to see. So now, the important thing to realize about today's presentation is that these condition codes here, and I'm going to tell you what the naming convention is in a moment for those, they can be set in 2 different ways. So some arithmetic instructions will set them. And then there's some other instructions called compare and test that we're going to look at today that actually set these quite explicitly. So arithmetic instructions will implicitly set them, and compare and test will explicitly set them. And so you'll see the different cases here as we go along. So an important thing to remember here is when we say set, we mean change a condition code from a 0 to a 1. And so keep that in mind as we go along. I'll keep saying these codes are going to be set. That means they're going to be set to a 1. All right, let's first look at implicit setting by a particular arithmetic instruction as an example. So the names of these 4 single bits in the CPU, these condition codes, are derived from this idea. So CF stands for carry flag. And this is used if the type of instruction that we're working with is working with unsigned variables here in the source and destination. The 0 flag is used for both signed and unsigned, and that's what the ZF stands for. The SF stands for sign flag. This is used if the 2 variables are signed, and the OF stands for overflow flag. That's also used if the 2 variables are signed. So for example here, suppose I had this instruction where I was adding 2 values and then putting the result of adding those into this destination. That could be a line of C code that looks something like this, for example, T equals A plus B. So what happens is when this instruction gets executed, these bits could get set to 1. And here's how they could. So if A and B are unsigned and adding them resulted in overflow, then this CF bit would get set. If A and B result, when you add them together, in 0, so suppose you had -5 and +5, then when you added them they equal 0, then the 0 flag would get set. Now, if the source and destination A and B are signed integer values, then SF would get set if the result of adding them together is negative, less than 0. And the OF, the overflow flag, would get set if overflow happened. And recall that overflow can happen when A is greater than 0 and B is greater than 0, but the result of adding them is less than 0. The other time that overflow can happen is when A is less than 0 and B is less than 0. And when we add them together, the result is greater than or equal to 0. So when these things happen, then the overflow flag will get set. What's kind of interesting to note about this is that LEAQ, when being co-opted for doing math, like you've been seeing in previous presentations and doing in the activities, that instruction does not set any of these flags. So the compiler writers will sometimes not use LEAQ if it's important to be checking whether a particular operation overflows or not. Okay, so now the key here is that when we add and do this instruction, these codes may get set. And that is what we call implicit setting of these codes. Okay, now what then can happen is the next instruction may use those. And so depending on what the compiler writer chooses to do about certain situations, it's possible to check these flags. We're going to see a much more when we talk about explicit setting of these, we're really going to see how the values of these condition codes are set. So let's look at that example. So explicit setting of these conditional codes is done by two different instructions: compare instructions and then followed by set instructions. Their explicit setting is also done by another one called test, which we'll see as well. So here is explicit setting using compare. So here's the compare instruction, CMP, and then here's our cue for traditionally 8-byte long source and destination. Now what happens here though is we have really two sources and no destination, because no destination is actually set. This compare instruction is really used to set these condition codes. And so compare is as if you're taking source 1, which notice is over here on the right, and source 2, and subtracting them. So if we had to compare B to A, it would be like computing A minus B. And then the result of that computation, A minus B, is used to set these flags. So again, if the two of them were unsigned, that basically the carry flag gets set if they resulted in overflow. If the two of them are equal, the 0 flag will get set. If A minus B, in this example here, is less than 0 and A and B were signed values, then the sign flag would get set. And a similar thing happens when you compute A minus B and check for overflow. And these are the conditions that are going to be checked for there. And so basically you'll notice that if A and B are unsigned, then the carry flag comes into play. Regardless of whether they're signed or unsigned, the 0 flag comes into play. And if A and B are signed values, then SF and OF are used. Okay, so you're probably wondering, well, okay, so compare. Big deal, we're setting all these flags. The compare is then used with other operators, other instructions, to determine the relationship between A and B. And so that's what we're going to see in a moment. Now, the other instruction that does explicit setting, but only of ZF and SF, is an instruction called test. So here, with test, what we're doing is the CPU is going to do A and B, bitwise and. And it's not going to set a destination, but it's going to set the 0 flag when A and B equals 0. And it's going to set the sign flag when A and B is less than 0. Now, this one is kind of interesting because it's useful and used a lot when checking if a value is equal to 0. So in this case, instead of having two different values, A and B here, we'll often see in our code a test queue with A, comma A. And what that means is if we AND a value with itself, the only value that will equal all zeros when it's ANDed with itself is 0. So test queue will often be used to see if the 0 flag got set when the same value is ANDed with itself. If it did get set to 0, that means the original value was 0. Try this out. Try any values A and B and see that if you AND them with themselves, the only one that turns out to ever be 0 is when 0 is ANDed with itself. So that's where this one gets used, and you'll see some examples in the activity of the use of this. Okay, so now we've got these instructions, compare and test. And what we want to see is really, well, how are these things going to get used? And in order to see that, I want you to remember that we can access the very lowest order byte of any register by using these register names that I've highlighted here. And so remember that those are the register names that are going to come into play when we're using these compare and set instructions. And the test, compare, test, and then set. So let's see how this is going to play out. So we've got another instructions beside compare and test called set. What that does is it sets the lower order byte of a destination to 0 or 1 based on these condition codes. And it doesn't alter the rest of the bytes. So here are our most common set instructions. And so you see here we have a set E, set NE, set S, set NS, and so on. And then we have the way that the lowest order byte of some register here is going to get set is based on the value of the condition codes and then these expressions using those condition codes. And the easiest way to understand this is to start seeing an example. So here's an example, set E. And you notice here is the lowest order byte of this register is called AL. So what it's going to do is set E is going to look at the 0 flag. So you have to use set in conjunction with compare, sometimes in conjunction with test, but most of the time we'll see it in conjunction with compare. And so assume we've done a compare, and now if the 0 flag had been set, then this set E is going to set the AL register to a 1. So let's see this in action even further. Now, you're not going to need to memorize these expressions for the condition codes. It's really going to be easy enough for you to use these letters at the end of the set to be able to see what's going on in your code. I'm going to show you this one that's one of the most complicated ones, just so you can see how it works. But you won't have to memorize these. Knowing these will be good enough. And this is kind of the beauty of how these set instructions have been set up. So let's look at a code example now. So here we have a very simple function called GT, which takes in a long x and a long y, and it's simply going to return whether x is greater than y. You're going to see several of these in the activity, and you're going to play around with different ones and then look at this corresponding assembly code that goes with it. So you'll notice here for this one line of C code, we now actually have 3 lines of assembly code. This is the kind of thing that you're going to start seeing as we get more complicated types of instructions. So let's have a look at this. So first we have a compare. And remember now that RDI holds the X and RSI holds the Y. And you will notice that RDI is over here and RSI is over here. And that's probably the main thing to remember. I'm going to bring this up again later after we go through this, just so you remember that. But X is here, Y is here. Now, so the compare is being done, and that compare from the previous slide that I had up is doing this. It's computing A minus B, and then instead of setting a destination here, it's simply setting the different flags. And then the next set instruction is setting this single byte register, AL, to a 1 when X is greater than Y. And then, so in order to do that, it's using this combination of the condition codes, those different flags. So this combination, this expression, looks kind of crazy. We're going to see in a minute how it's able to make that work. But for now, we can say this works. If we want to know if X is greater than Y, we're going to use set G, and it's going to give us the right value here in AL. And set G is going to do this by looking at the condition codes after doing this compare. And we'll see, I'll take you through this in detail in a moment. But for now, believe it that when we compare X to Y, this AL is going to be a 1 if X is greater than Y. And then the next thing we need to do is this AL is only that one least significant byte. So compare and set is almost always followed by this move ZBL that we saw last time. And that's so that we can zero out the upper 3 bytes of EAX, because this code is supposed to be returning an int here, and it's supposed to be returning whether X is greater than Y. So it's supposed to return a 1 or a 0. So we want to zero out everything in EAX. And then remember that the register ending in AX is the return value. And so when this returns the result of evaluating X greater than Y will be in EAX, and the top part of it will be zeroed out. So that's how these 3 instructions are used to carry out this one line of C code there. All right, and so so there we have it. Here was our relational operator, and here was the instructions that were used to get it. Now, the key thing here I'm going to bring up again is that X and Y are swapped in this compare when followed by the swap. And so the X is over here and the Y is over there. That is the most important thing you're going to have to remember when looking at these relational expressions. So remember this, that these two things get swapped in that compare statement. Okay, so now that move that's in there, just to remind you again, is zeroing out those highest order bytes. So when we return whether or not x is greater than y, we want to make sure that these bytes here are 0. And so that's what's going on with this final move ZBL instruction there. Okay, so that's what's going on with that one. Now, let's go back and really look carefully at how this set G is doing its job. So here we have the instructions again for this function. Now in this case, x and y are signed long values, the way this code was written. Okay, so let's suppose that x and y were 10 and 5 respectively. So x minus y is 5. Okay. Now the result of doing that then is a positive value, and these are signed, and so the carry flag doesn't even come into play because these are sign values. So the carry flag is going to remain 0. Then these two are not equal to each other. So you see here that the ZF flag will also not be set. It will remain 0. Now, A minus B, 10 minus 5, is not less than 0. So the sign flag remains set to 0. And in this case, there certainly is no overflow going on for this particular example, 10 minus 5. So the overflow flag will also not get set, right? So that's this one down here. So now we're going to evaluate all of these flags, none of which in this particular case got set by doing 10 minus 5, right? So now that then looks like this for set G. This is the expression that's going to get evaluated for set G. So how does this work? Here's our exclusive OR truth table, so you remember that. 0, exclusive OR 0 is going to be 0. So this part is going to be 0. And then when we complement that or flip the bit, that's going to be a 1 on this side of the bitwise AND. And then if we complement 0, that's going to be a 1. So this is going to be 1 and 1. That then comes out to be 1. So indeed, set G here is going to put a 1 in AL, and it is true that 10 is greater than 5. Now, as an example, to just work through this yourself, I suggest you try the other one. So here, x is less than. So in the end, when you work through this, you should end up with a 0 out here using this expression and realizing what flags would be set. And similarly, if the two of them are equal, you should come out with a 1 out here. And so work through these on your own if you'd like to. The good news is that as long as you know that you're comparing this to that, set G will tell you whether this is greater than that. So the main thing is to know that. You're not going to be tested on knowing each of these individual expressions for the condition codes. You're mainly going to be you're going to need to make sure you understand how that set G is used with this compare to tell us whether that is greater than that. So that's the main thing you're going to have to remember. So now another thing I'd like to point out is these two down here at the bottom, set A and set B. So set G makes a lot of sense. It's used for sign values. We just check if some sign value is greater than another sign value. And then we have a greater than or equal to that we use for greater than or equal to, less than or equal to. But down here now, if we have unsigned variables, the instruction set assembly language designers had to come up with some new versions for these. And so what they did was set A and set B. So A means above and B means below. And there's also actually a set AE, so above or equal to, and below or equal to. Now these are used with unsigned variables. And so what I'd like you to do when you go to the activity now is try some unsigned variables. I'm showing that right here, so that you also see these set A and set B being used along with the sign values. So I want you to go ahead, try only part one of this activity. There's two parts to it. We're just going to do part one. And you'll want to study the code fairly carefully, like I've just gone through with you now, and try different relational operators. Besides greater than, try all the other relational operators you can think of, and look at the code that gets made from that, the assembly code. And then also try different lengths so that you can see how the B, W, L, and Q get used. And then definitely try unsigned variables and looking at the relationship between those so you can see how those are used as well. So go for it. Try the activity called 5-control, but just do part one at this time.